Hello everyone, welcome to my physics corner. I am Vonnie from class XE Pagi, and in this video I'm going to explain about the properties and the natures of light. So, what is light? In physics, light is a form of energy which is radiated from a source and it is detected by the eye. Light is a member of the electromagnetic spectrum which is visible to our eyes. Light is also a form of energy that can carry heat. In physics, we use straight line with arrows to represent the path of light. The arrow indicates the direction in which the light travels. Such lines are called as light rays. A beam of light is actually a bundle of light rays. Next, the electromagnetic spectrum. The electromagnetic spectrum consists of 7 components: gamma rays, X-rays, ultraviolet ray, visible light, infrared, microwave, and radio wave. The EM waves are arranged from the highest amplitude frequencies and the highest energy with the, however, shorter wavelength to the lowest energy amplitude frequencies with the longest wavelength. In this slide, you can see the parts of wave train. We have crest, throat, amplitude, and wavelength. So, number 1, the nature of light. The first one is light as a particle by Sir Isaac Newton. With the corpuscular theory, light consists of tiny particles which travel along a straight path, which is divided into, the first one is reflection, or the bouncing of light, and the second one is refraction, or the bending of the light. Reflection is the change in direction of wave passing from one medium to another, or from a gradual change in the medium. The second is light as wave by Christian Huygens. With the wave theory of light, light is a range of frequencies of electromagnetic wave whose wavelength vary from 400 nanometers to 700 nanometers. The example of light as a wave is the rainbow. Rainbows have what you call light spectrum. Light spectrum is the many different wavelengths of energy produced by a light source. Light is measured in nanometers, and each nanometer represents a wavelength of light or a band of light energy. Visible light is the part of the spectrum from 380 nanometers to 780 nanometers. Dispersion refers to the separation of white light into different colors of a spectrum due to its refraction as the light passes from one medium to another. As you know, rainbows have 7 different colors, and each color has a different wavelength and frequencies. The red color has the highest wavelength, which is 700 nanometers, and also the lowest frequency, which is 4.29 times 10 raised to 14 Hz. While the last color, which is the violet, has the lowest wavelength, which is 400 nanometers, and the highest frequency, which is 7.50 times 10 raised to 14 Hz. The next slide is the color addition and subtraction of light. Red, green, and blue are the 3 primary colors of light. As you can see in the diagram, if we add red color with the blue, it will produce magenta. If we add green with blue, it will produce cyan. If we add green with red, it will produce yellow. If we add all the primary colors, it will produce white light. Same when we add all the primary and the secondary colors together, it will produce the white color.
I can take another color such as green, and I can ask myself what would happen if I mixed green light with red light. Well, if I turn it on just very, very low at first and bring up the intensity, I can see that the green light and the red light overlap in this region, and when they do, they create yellow light. So now I can turn on the third color of light and mix it in, the blue. As I bring up the blue light, I see the regions of overlap between green and blue and red and blue, and in the region of overlap of all 3 of the lights, I see a combination that looks very much like white light.
Next, we have the color subtraction. It refers to the removal of some frequency of the light as white light passes through the filter to produce a new resulting color. Now you can see that there is a red filter in front of the colors of light, which is white light. And the colors that can pass through the red filter is only red light. Next, in the upper diagram, what if we place yellow and magenta filters in front of the white light? The yellow filter will absorb the color, leaving red and green to pass through. Next, the magenta filter will absorb green light, and the result is the red light. In the second diagram, if we place red and green filter in front of the white light, what will happen? The red filter will absorb colors, leaving red to pass through. When it reaches the green filter, the red color cannot pass through. Hence, the resulting is black, or the absence of any color of light.
So the trading cards, the transparencies and the reflective cards, have on them a graph, in this case the percent transmission versus the wavelength, and I can get an idea of what wavelengths of light will be transmitted most intensely through this color of filter. So let's try this. We'll start with red, so I'll turn off the green and the blue light, and I'll take out one of the filters. I think I'll start out with a red filter, and I'm going to cover up the light, the red light, with the red filter. Let's see what happens. And that is the red light covered with the red filter. Next, I'll experiment with the blue light that we saw a minute ago, with the blue transparency here. This blue filter I'll go and put in front of the red light, and it transmits virtually none of the red light that we can see. Okay, so that's an example of the filters, the red and the blue. Now let's see what happens when we reflect light from different colors of cards. First, let's try red light on red light. So I'll put this reflection card with, you can see now it has a graph of relative intensity of reflected light versus wavelength. I'll put this in front of the red light, and it reflects red light. I'll use a green card. I'll put the green card in front of the red light. And now, I think just out of curiosity's sake, I'll put the green card in front of blue light, see what happens. So here is the green card in front of blue light. Now, we also have, in this optional set of cards, two yellow cards, one of which is just regular yellow paint or pigment, and the other of which is fluorescent yellow. So I'll put the regular yellow card in front, and then I'll follow that with the fluorescent yellow card. So regular yellow versus fluorescent yellow.
In this slide, there are three equations used to calculate the frequencies, wavelength, and energy carried by the light. The first equation we have is speed is equal to wavelength times the frequencies, and the second one is speed of light is equal to wavelength times frequency. The speed of light is 3 times 10 raised to 8 meter per second. And the last is energy is equal to Planck's constant times the frequencies. The Planck constant is 6.63 times 10 raised to negative 34 joule second. Now let's solve this together. Determine the frequencies and energy carried by the red color of light. From the previous slide, we know that the wavelength of red color is 700 nanometer, or 7 times 10 raised to negative 7 meter. Next, we also know that speed of light is 3 times 10 raised to 8 meters per second. And the Planck's constant is 6.63 times 10 raised to negative 34 joule per second. Now let's find the frequencies. We can use the first equation to find the frequencies, which is speed of light is equal to frequency times the wavelength. We can transpose the wavelength to the right side, hence it becomes F is equal to C divided by the wavelength is equal to, then we input the numbers. 3 times 10 raised to 8 meter per second divided by 7 times 10 raised to negative 7 meter. And the result is 4 times 10 raised to 14 hertz or more per second. Next, to find the energy, we can use the third equation, which is E is equal to H times F. As I said before, the H is equal to 6.63 times 10 raised to negative 34 times the frequency, which is 4 times 10 raised to 14. But the result is 2.65 times 10 raised to negative 19 joule. Number 2, the characteristic of light. The characteristic of light is divided into 4: reflection, refraction, diffraction, then interference. First, I'm going to explain about the reflection. So, as I said before, reflection is the bending of light. The law of refraction are the incident ray, the reflected ray, and the normal lie in the same place. And the second one is the angle of incident is equal to the angle of reflection. There are 2 types of reflection. The first one is regular refraction. It occurs in the smooth surface. And has light rays that are parallel to each other. And the second one is diffuse reflection. It occurs in a rough surface and light rays are in random direction. Next, you have the diffraction. Refraction is the ability of light to pass through slits or barrier. This small hole right here is called as slits. Next, interference happens when the 2 or more waves overlap each other. The light passes the slits. And the light overlap each other. Next, there are 2 types of interference. The first one is the constructive interference. It occurs when the maxima of the 2 waves add together so that the amplitude of the resulting wave is equal to the sum of the individual amplitude. The second one is destructive interference. It occurs when the maxima of the 2 waves are 180 degrees out of phase. A positive displacement of one wave is cancelled exactly by a negative displacement of the other wave. The amplitude of the resulting wave is 0. In this slide, we can see the picture of both constructive and destructive interference. Now, let us solve this question together. Given the two adjacent plane mirror AB and mirror BC, which form an angle of 120 degrees as shown in the figure below, if a beam of light strikes mirror AB at angle 20 degrees from the mirror, A. Find the angle of incident AB, and B. Find the angle of reflection of AB. In this slide, I have already drawn a diagram. We already know that the given angle is 20 degrees. From the 20 degrees, we can find the incident angle by 19 degrees minus 20 degrees, which is equal to 70 degrees. Now, we have to solve for the angle of reflection. We can start by finding the x. Back to the light at the mirror AB, we have already learned that the angle of incidence is equal to the angle of the reflection. So we can already know that the right side of normal light is equal to 70 and the 20 degrees. We also know that the sum of the three angles of the triangles equals to 180 degrees. Therefore, we can solve the x by 180 degrees minus the 120 degrees minus the 20 degrees and it equals to 40 degrees. Same as the mirror AB, we solve the angle of reflection of BC. The angle of reflection is equal to the angle of incidence. So 90 minus the x, which is 40, is equal to 50 degrees. And then finished. We can now solve for the angle of incidence and reflection in the two mirrors. That's all for today. Thank you for listening and see you next time.